So good to review Quicksort. It was a homework, so that's definitely something that Ross would find tempting to ask a question about because you guys had kind of an involvement with it. So whereas merge sort does the recursive calls first and then merges, Quicksort partitions, which is a linear pass over the data, throwing stuff to the left and to the right piles of a partitioning element, and then recurses on those two piles. So we saw that a bad choice of pivot can cause n-squared behavior. But in general, like an okay choice of pivot, even separating out some constant, some fraction, is pretty good. It's a log of something. So when we randomize, we can kind of randomly pick a partition or randomly choose an element to get swapped into the position that we're going to use as the partition. When we're doing the analysis of the running time here, we have to kind of think about how many comparisons we're going to end up doing, and we know that the likelihood of having to compare two elements can be calculated like so here. 2 divided by the range between those elements in the final sort. A little clarification, so randomized algorithms, when we talk about a randomized algorithm, they have an expected bound. And then sometimes people just kind of confuse this because it kind of sounds like the amortized. So when you're thinking of amortized analysis, think we're kind of averaging. All right, we're going to take cases that are kind of cheap and cases that are expensive, and we'll kind of average them. All right, and that's the amortized analysis aspect of it. But with randomized algorithms, we're looking at those expected bounds. And so, for instance here, if we're going to sort some alphabet letters, D, E, F, G. So if we're going to sort some alphabet letters, we know that initially they'll kind of come in jumbled, so, who knows, we're just going to put some question marks. They came in jumbled, but we know at the end they're going to be in sorted order. And so then we can start looking at pairs of elements like this pair, so C and D. And because they're right next to each other in the sort, there would be no way of knowing where they'll sit finally without directly comparing them. So since they are since they're a closest pair of elements, they will have to get compared at some point in order to produce a sorted array. There's just no way around that. So these two will definitely get compared at some point. These two will definitely get compared at some point. And these two will definitely get compared at some point, so on and so forth. But now if we look at elements that are a little bit further away, like say C and E, they may still get compared because one of them is chosen as the pivot at some point, where the other one is still there. And so they will get compared. But possibly D will be chosen as the pivot. And D will be compared to both C and C and E will never be compared to each other because they will have gone to different sides of the recursive call. Okay? And so whenever we're kind of looking at these things, there's some range, or we could talk about maybe B to E, because that's kind of more interesting here. So with the range of B to E, there is going to be a first element within this range that gets to be a partitioning element in the algorithm. It's like we're throwing a dart here, and we know that at some point a dart will have to land in this range. When the dart does land in this range, what is the probability that that first dart will be one of these guys, so that B will be compared to E? Or what's the probability, 1 minus that is the probability that one of these two, neither of these two will be the partitioning element. So maybe D will be the partitioning element first among all of these 4, which means that D will be compared to these guys, but then now B and E will go to separate recursive calls, and they'll never be compared because they'll just be down separate paths in the recursion tree. Okay, so it's always the chance of these two being compared is always 2 divided by, that number of elements in their range. So there's B and E have a 2/4 chance. And so like A to F would have a 2 out of 1, 2, 3, 4, 5, 6. And A to G would be 2 out of 7, 2/7. Okay? And so now we see that we have an expectation of elements being compared to each other based on how far away they are in the final sort, in the done sort. So now we can kind of tally up all these things. So for pairs that are right next to each other, so like A and B, that's like a 2/2 chance, essentially, that they'll be compared. All right, so 2/2. And then how many pairs do we have? How many adjacent pairs do we have? 1, 2, 3, 4, 5, 6. So 1 fewer than the number of elements. So n minus 1. So there's going to be n minus 1 of these pairs of adjacent elements which have a 100% chance of being compared to each other at some point. So now, though, when we look at things that are have a little gap between them, so they have an intervening element, they'll have a 2 out of 3 chance of being compared to each other. And how many of them are there? There's these two, these two, these two, these two, these two. We kind of ran out 1 short, so it's even fewer. It's n minus 2 of pairs that are a little bit farther away from each other. And so similarly, pairs that are that far away will have a 2/4 chance, and then 2/5, and then so on and so forth, down to at the very bottom at the limit here, we'll have things that are, like n minus 1 away from each other, and then they have a 2 out of n chance of being compared to each other. And that's that first recursive call, the very first call to partition in Quicksort. Either A or G will be the partitioning element, and so they will get compared to each other. Or if it's anybody else gets to be the partitioning element, then A and G will never be compared because they'll go to separate sides. Okay, so this goes down to 2/2, 2/3, down to 2/n. This is growing smaller all the time too, so it's n minus 1, n minus 2, n minus 3, so on and so forth, down to 1. There's only 1 pair of elements that has such a small chance of being compared. And so now each one of these, this is the probability or our expectation of them being compared, of a comparison happening. And here's how many pairs exhibit that relationship. So it's kind of like we'd like to do multiplication. We'd like to say this times this, and then plus, and then this times this, plus, this times this, plus, this times this. So we'd like to sum all these expectations up. So one way to kind of come at this is let's first pull out all the 2's. Okay, let's just kind of factor those out to the front. So I'm just going to pull out a 2. Then this will be the harmonic series, right? So like 1/2, 1/3, 1/4, 1/5. And then now when we think about kind of taking the harmonic series and we're kind of multiplying it by these smaller and smaller elements, we'll have that, we'll have kind of 1/2 n and then minus, and then this is 1/2, and then there'll be a 1/3 n is the next one, minus, and then 2/3, and then 1/4 n minus, and then 3/4. So you can kind of see where this is going. At some point we'll get down to 1 over n times n minus, and then these numbers kind of being in any indication, it'll be n minus 1 divided by n. So now we can kind of see, and we're still trying to sum all these up together, and we've still got a big 2 that we've kind of factored out front. But if we look at this, there's the kind of a harmonic series multiplied by n. If we factor all these n's out, we would have n times, and then the harmonic series, so 1/2 plus 1/3 plus 1/4 plus ... plus 1/n. And then we would have all of these things. Now notice these, the smallest of any of these kind of like additive constants, like this one is tiny, or sorry, this one is kind of large. It's almost 1, it's like 99%, it's like 0.99 or something, because it's like 99 out of 100. So it's almost 1, it's a pretty big number. The smallest number is 1/2, and then they range in between these two sizes, 1/2 and almost 1. So we know that, and there's n of them. So we know that this is going to be bounded between, it's going to be somewhere between 1/2 of n and 1 times n. So that's just kind of a constant difference. And so I'm just going to kind of just say minus n. There's some constant in front of this minus n. It's like, n times 0.75 or something. But we could either hurt our case, rounding them all down or rounding them all up to the highest or the lowest. And we'd see it's just the constant factor. So what we'll end up having here is then the harmonic series, which we know sums to log n times n. So n log n, and then minus some funky constant minus an n. And then of course around the outside there's a big times 2 around all this too. But so if we kind of ignore constants and this, kind of like little subtractive thing here, we get the core of the expectation, which is that it'll be growing in proportion to n log n with randomized pivot selection. And I think that's pretty good for this chapter, yeah. So just watch out because it was a homework, so it definitely seems like something that he could ask you to kind of show a small example on. Good.